a very short introduction into particle filters in general, or especially particle filters used for Monte Carlo localization, so for localizing a robot in an environment given that we have a map. We assume typically we have a map, something like the occupancy grid map that we had before. We want to estimate the position of the robot in this grid map. What we did so far in order to do the state estimation, we used Gaussian filters, the Kalman filter, for example, to estimate a probability distribution. And this probability distribution was supposed to be Gaussian. And as if we have a Gaussian distribution, and let's say our models are not too nonlinear, use the EKF. It's a good approach to do that. If your underlying distribution is Gaussian, and if your models are not dramatically nonlinear. This is the case, EKF is a fine choice. What happens, however, if we have arbitrary distributions? So we want to leave the Gaussian world. Let's say we have a distribution which looks like this. How can we actually solve this problem? And how can we represent such an arbitrary distribution, or consider any arbitrary distribution you want? How can we use a different way for estimating the pose of the robot if we leave the Gaussian world? That's kind of one of the advantages or the domain of the particle filters, and they are very attractive techniques to do that. So the key idea of the particle filter is not to use a parametric form, so like a Gaussian, but to use a non-parametric representation of my distribution. And what the particle filter does, it uses random samples. And so let's say if this is my distribution and I generate, let's say, samples for the beginning, I can see these samples as points which live in my x-coordinate here. And the more samples I have in a certain area, the higher the probability of that area or region. And I may also assign a weight to those samples. So the bigger the dot here is, the higher the weight, and the higher the probability of the corresponding area. So here where I have that peak, I have kind of large bubbles. And there where the probability is very small, I have small bubbles. It's kind of the intuitive way for how I can see samples. In this example, they are, I think, more or less, or they're even not uniformly spread, but they can be randomly spread through the environment, those samples. It should not suggest that this is kind of a uniform spread in general. How can we do that? How do we represent the posterior? As I said, we represent the posterior by a set of samples. See every sample as a state hypothesis. So one possible explanation for the state. One possible state the system may be in. Just say, if you have 1,000 samples, it says either the world looks like this, or like this, or like this, or like this, 1,000 times, or like that. That's the key idea. And if you want to compute my probability distribution out of this sample set, just say, okay, what's the probability that the true state is within a small region? Just look into that region and count the number of samples that are in. The higher the number of samples, or the higher the weight of the samples in there, the higher the probability of the true state lies within that small area. It should be clear that you may need a large number of samples to represent the distribution well. The higher the dimensions of the function you want to estimate, the more samples you need. And if you have areas of large uncertainty, you may need a huge number of samples. In that sense, there's no free lunch. You are more flexible in what we want to represent, but this may come at a high computational cost. We consider a Kalman filter, which has whatever a variance of, in 1D, let's say you have a spatial phenomena of whatever 1 centimeter. If it's 1 centimeter, your standard deviation, or if it's 100 meters, you don't care. It's the same. You need the same computational resources. For samples, if you want to have a certain density of samples, you would need to have a dramatically larger number of samples if your uncertainty is very large. So that's a disadvantage of the particle filter. Okay, so these are the state hypotheses. This is X, and I typically have what's called an importance weight. So that's the weighting term. In the beginning, the weight can be 1 or 1 divided by n. So the same weight for all the samples, and I just need to count the samples which fall into a certain region. Otherwise, I need to count count up the weights which fall into a certain area. So if I do it that way and represent it in that way, the probability distribution that I obtain that this sample set represents is just a sum of all samples, the weight of the individual samples, and the Dirac distribution centered in the state of the sample. So again, Dirac distribution, it's a distribution which is 0 outside the state, it's infinite at the state, but the integral is 1. So it's extremely narrow, and so as you weigh, if the samples are normalized, it means the sum of all samples is 1. If you compute this term, you get a proper probability distribution. Of course, it's kind of very peaked. That's what the probability distribution looks like. But if you have a sufficient number of samples and you look kind of into regions for which you want to compute the probability, it's the same as if you would count the samples. But that's mathematically what the probability distribution looks like that is represented by a sample set. So is this clear what that means? Okay, so just try to explain it again. If I have n samples distributed over the space, I say, okay, for every sample, I have a probability distribution that this means it's a state hypothesis. The state is in that state, so it's has a high value in that state and is 0 anywhere else. And since I have whatever n samples, if they're all of the same weight, it's kind of 1 divided by n times the Dirac distribution centered in the position of particle 1, plus the Dirac distribution sampled in the state of particle 2, and so on and so forth. And if I change the weight, as soon as I make sure that the weight sums up to 1, that's the probability distribution that I'm maintaining. So I can use these particles or samples for functional approximation. So if this is a Gaussian distribution, that's a sample-based representation, how it looks like. Of course, the more samples I have, the better my approximation will be. And you can see here in the area of the mode, there are more samples concentrated and there are less samples outside towards the tail of my Gaussian. Or if I have whatever, this fancy distribution, I have a high concentration here and also a high concentration here and smaller concentration down there. Obviously here, from the particle representation, it's kind of probability 0 that anything is in this area. It's just because I haven't used enough samples. So the more samples I have, the better my approximation. And the question is now, how do we obtain those samples? How can we actually generate those samples? The thing is, it can be tricky. So there are some distributions for which I can sample in closed form. One example is the Gaussian distribution. And if I want to generate samples from a Gaussian distribution, that's one technique to do that. So just take 12 random numbers between minus and plus the standard deviation of the Gaussian distribution, sum all of them up and divide it by 2. This generates samples from a Gaussian distribution that is centered around 0 with this standard deviation. More details on that you can find in the probabilistic Introduction to Mobile Robotics course when it's talking about how to generate samples, how to do samplings. You find an explanation for that, also graphical examples, how you end up with this distribution. Just repeat that. The important thing for me here is for certain number of certain distributions, like for example for a Gaussian, you can efficiently draw those samples, generate those samples. But the question is, what about the other distributions? Whatever if we have some weird odd distribution. How do we generate samples from this distribution? And one technique to do so is importance sampling, and it relies on the so-called importance sampling principle. What the importance sampling principle tells us is, let's say we have a function f, which is also called target distribution, and we want to generate samples from this target distribution. Unfortunately, this target distribution has some form where we cannot generate samples from in closed form. So how do we do that? The importance sampling principle tells us that we can use a different distribution, which is called a G, or the proposal distribution, or sometimes called pi later on. And we can actually generate the samples from this other distribution, from the proposal. Let's say we take a Gaussian at the proposal, which is different to the target, but we just use another distribution. So we generate samples from this proposal distribution, and then we can do a correction taking into account the difference between the target distribution and the proposal distribution. And this introduces a weight, so the so-called importance weight. And this is given by evaluating the value of the target at the sample location divided by the by the proposal distribution. And this gives me a weight. So if I have my example over here, if this is my proposal distribution, the red one, the Gaussian, and this is my whatever target distribution, what I do is simply I generate samples from this Gaussian distribution. So the spacing in x, the x location drawn here are from the Gaussian, but then I reweight those samples by the difference between both distributions. So if there's a big difference, I will get here a large weight, or depending on the ratio. So a large or extremely small weight. In this way, I kind of correct the samples and I obtain samples which follow my target distribution. That's what the important sampling principle tells me. I think I said before that's important sampling. That's not exactly true. But important sampling uses this to generate samples here. Okay. And what the particle filter now does, it uses those samples to represent the posterior and uses exactly the important sampling principle to update a belief. So it's a recursive based filter. It is a non-parametric recursive based filter. That means we do not maintain, for example, a closed form distribution like a Gaussian distribution. We take those random samples as my representation of the underlying distribution, and I update my samples based on the motions that I have and based on the observations that I obtain. And it has two steps, again, a prediction and a correction step. The prediction step draws samples from the so-called proposal distribution. This is a distribution I can easily sample from. And in terms of localization, I typically use my motion, my odometry, as a proposal to generate the new samples, taking into account the motion of the platform. And then I take my observations for doing the correction. And therefore, if we do this, we see the connection between the prediction and the correction step. And the important thing is the more samples we have, the better is the estimate. So the particle filter has kind of three main steps. The first thing is it samples from the proposal distribution. So this is kind of, it generates samples from my proposal pi over here. This is a distribution which I choose as a designer and from which I can sample efficiently. For example, a Gaussian distribution. What I then do, I then compute the so-called importance weight, which takes into account the function that I actually want to approximate. The only thing I require here that I can evaluate it point-wise. So I can, for every point in space, can evaluate this value and divide it by the proposal. And this kind of does the correction, telling me what's the difference between the proposal that I chose to generate samples and the function that I want to approximate. And this gives me the so-called importance weights. It's kind of the correction for the fact that I actually sampled from the wrong distribution. And then there's a third step, which is a so-called resampling step. It's kind of a sampling with replacement. So I have my weighted sample step after step 3, and then I just draw J samples out of that with replacement, and the probability of drawing a sample is proportional to the importance weight. You can see this, informally speaking, as kind of a survival of the fittest. So it's quite likely to pick a sample with a high weight. These are kind of the good samples where the approximation was good. And I'll leave over and let those die which haven't been drawn, which are more likely to have a small weight. And this way, I kind of focus my sample set on the likely parts of the state space. Okay, let's look to the algorithm. How does the particle filter algorithm look like? I have my old sample set as an input, I have my controls, and I have my observations. So same input as the base filter. Previous belief, control, and observation. So I say, okay, I start two new sets. So this is kind of the predicted set and the corrected set. They both start with empty sets. I iterate over all my samples in my previous belief. And I obtain a new sample for J by sampling from my proposal distribution. What in practice happens in localization is that I take the sample out of my previous belief, apply the motion forward, and then sample around that area. Then the second, for every sample, I compute the correction by taking the target distribution divided by the proposal, and I add that to my predicted sample set. This is what I do for all samples. And then this is what you see down here is a resampling step. So we draw a particle I proportional to its weight and include it into my resulting sample set. And this is what I'm going to return. Okay, so this was kind of more the general particle filter. Let's look specifically into Monte Carlo localization. It's just a specific instance of particle filtering. So what we do in here is each particle is a pose hypothesis of the robot. So it's an x, y, theta state the system may be in. We want to estimate where's the system at the moment. X, y, theta. What I typically do in Monte Carlo localization, I choose as a proposal distribution, I choose my motion model. So how does the robot's motion, ut, changes the state? So let's say I take my sample out of every sample out of my previous sample set, and then let's say the odometry said the robot moved a meter forward. What I do is I take this sample and move it a meter forward, and then may add some sampling noise around it. But that's basically the step that I do. I take every sample out of my previous sample set and apply my motion model in a sampling fashion. I sample from that model. And this generates me the next generation of those samples. And this is also one advantage is that I don't need a linearization of my motion model in this case, because it can have an arbitrary odd function because it just propagate one state through it and compute the new state sampling from that. And then I do the correction step, and the correction step takes the value of my target distribution, which is actually the same distribution we used in scan matching before, the likelihood of the observation times the likelihood of my odometry, it's my target distribution, and divided by the proposal, so by my odometry. And I obtain this correction, so it's exactly my observation model. And I have to say here, this is a very special case of the particle filtering, because if I use my odometry as my proposal distribution, my odometry model, then the correction is a term proportional to the importance weights. And I'm free to choose this distribution, my proposal. If I choose a different proposal distribution here, I will end up with a different correction term, because it's given by target by proposal. So I completely see that the step from the importance sampling principle to this slide over here may be a little bit quick. It's kind of a longer derivation which shows if you use the motion model as your proposal, that's your final observation model that you're going to obtain. And so we can derive the particle filter algorithm for localization. So this is exactly the same algorithm we had before, except that we have changed those two lines which are underlined in red in here, which is my odometry motion model from which I sample, and the observation model for doing the correction. And if I do that, that's what I'm going to obtain. So what you see here is samples spread all over the place. So all these red dots are samples, saying that's one possible pose where the robot is at the moment. In reality, the robot was here, starting over here, and moving in this corridor. That's the path the robot took. This illustrates currently the best estimate. In the beginning, it's random, because it's just one particle, because all of the same weight. And what you see here in these blue lines are kind of the sonar readings that the robot actually perceived. So these are the sonar scans. And what we see right now is a number of prediction and correction steps and resampling steps which evolve this state. So we propagate all samples forward according to the motion of the robot. We weigh them, and then we do the resampling step. In every resampling step, kind of the bad particles are more likely to die out, and the good particles are more likely to survive. Okay, if I start that video now, you see what happens. So the state is updated. You see this particle cloud moves a little bit. That's the motion of the robot. You can see after a few steps, the system identified that the robot must be in the corridor, because that's the area which is best in line with the observations. We have now two states, here or here, because the corridor is symmetric. So there's no way to figure out which one is better. until the robot goes into a room and can say, okay, the observations fit to this room and not to this room. So these samples die out and the sample set survives over here. And that's kind of a nice thing because, as you have seen, you can, during the estimation process, you can have multimodal distributions. You can say, I'm either here or here, and only until after I've seen enough information, I can actually tell where I am in reality. And there's an advantage if you do what we call global localization. So you start from having no or uniform initial guess. That's a strong advantage of this particle filtering techniques compared to things like, or techniques like the Kalman filter, which has one mode. You could, of course, start with a Gaussian distribution which is close to infinite standard deviation, or variance. But you can't maintain multiple modes over time. So there's something which actually doesn't work that well in practice. Okay. A few words about the resampling step, because it's one of the steps which often sound a little bit odd to people. So why do we actually do that? That we have our sample set with the weighted sample set, and then I just pick out n samples, draw n samples with replacement, and the likelihood of drawing a sample is proportional to the weight. Why do I do that? The thing is that the first thing we do is, the first reason why we do that is because we have a finite number of samples. As we have a finite number of samples, we want to concentrate those samples in the kind of the regions of the state space which are substantially above zero, having zero probability or density which is above zero. Because it can happen that, let's say, we make a few wrong decisions and the particle go into areas which have basically zero probability. If we have an infinite number of samples, we don't care if we have a large number of samples going to these unlikely regions, as long as we have enough samples in the areas with high likelihood. But in all practical applications, we only have a finite number of samples we can represent on our computer. So what we do is we kind of let the bad ones die out and use the sample to actually represent samples in the high likelihood areas. You can see this as a kind of survival of the fittest, or mathematically sound survival of the fittest principle. And so this kind of trick avoids that you have a lot of samples which go to this basically zero probability areas. And so this is needed whenever we really have a limited number of samples. And of course, the more samples we have, the better our approximation gets. But if we don't have infinite number of samples, we need this resampling step. And in practice, this resampling step is actually essential. So if you don't use the resampling step, you won't be able to track the pose of a system over long periods of time, because your filter will simply diverge and you won't have any samples which represent the likely areas. Every sample in the sampling process makes an error, and these errors typically accumulate. So there's no way for recovering it unless you have an infinite number of samples or you do resampling. Therefore, for practical application, resampling is really important. You can actually illustrate resampling. How can you actually implement that? You can implement that with the so-called the roulette wheel. So what you have is you have a roulette wheel, and the size of the buckets are proportional to the weight. And you take the ball, put it to the roulette wheel, and you take, if it ends up, let's say, in the bucket W3, corresponds to particle number 3, weight 3, you pick sample 3 and put it into your new sample set. And just you repeat this process n times. So you say, turn the roulette wheel once, you end up here, do another one here, here, and you continue like this. It's also called roulette wheel sampling. That's a standard approach to do that. You can do that quite efficient, or medium efficiently. Yeah, there are more efficient ways, but it's not too dramatically bad. And so if you arrange this set here with the binary search, so with an array you can do binary search in to find the distribution, then you can do that in j log j. So you need to repeat this process j times if you have j samples, and finding which sample corresponds to the bucket that you have chosen, you can do in log n with binary search here in log j. So j log j. So if you have 1 million samples, you have 1 million times log 1 million. It's the number of proportional to the number of operations you need to do. There's, however, a better way to do that. You can also use the roulette wheel. And the thing is, what we take now here is we take a uniform spacing of my called balls or pointer that I use, which points to my bucket. And what I do is I just turn the roulette wheel once. And then I pick the sample which corresponds to the bucket to which these arrows are pointing. So I just draw one random number, and I obtain samples which are chosen according to the importance weight. And this is something which is called stochastic universal resampling, also low variance resampling. And it has certain advantages. The first advantage is that you can actually do this in linear time, because you just draw one random number and then you iterate one through the buckets to find the corresponding buckets. The other advantage is what it does is if we have a set of samples and they all have exactly the same weight. This can happen if the observation doesn't help me to identify which sample is better than another one. Well, this will guarantee that we obtain exactly the same sample set than we had before. If you would use this technique, this wouldn't be necessarily the case. So maybe a sample gets chosen twice and one is simply not chosen. However, if all samples have exactly the same weight, there's no way for me to say, oh, this particle is better than, or this sample is better than another sample. So I should keep my sample set as it is. And therefore, this introduces the lowest variance into that process. And therefore, this is actually the technique that you should use. I also put the algorithm in here. I don't want to go through that algorithm. But the important thing is that it's kind of, you once process through the data set, and as one of the exercises that we will hand out next week, we'll cover this low variance resampling. You find the algorithm here on the slide, and your task will be to implement parts of a particle filter, and this will be one part of that. So what the approach in the end does, it just draws one random number as the starting point, and then iterates with adds to the cumulative weight 1 divided by n, kind of jumps always 1 divided by n through the roulette wheel, and always take the sample which corresponds to the corresponding bucket. So if you do that, this is another example, put all of that together. This was actually one of the first museum tour guide experiments where Monte Carlo localization, in the context where Monte Carlo localization actually was developed. So this is a museum, and you want to localize the robot where it is, kind of the top view of the museum. And you get an observation. So it has actually a robot with 2 laser range scanners, one looking to the front, one looking to the back. So it gives me the observation. Then we do a resampling step. So it's kind of the area is concentrated, motion update, sorry. And oh, these were 2 actually. Resampling and motion update. And then you take again a measurement. The weight is updated, resampling is done, you see how the particles die out, motion update is performed. You can see from here to here, when you do the motion update, the motion introduces noise. Because the motion introduces noise, and therefore the particles are spread out. This comes from the sampling procedure. Then you again take a measurement, do a weight update, so you see some samples are a bit darker than others. The darker, here the higher the probability. And then you do resampling, and then the unlikely states die out, and it concentrates on the more likely ones, and then you can actually continue this process and continue localizing the robot. It's kind of, this is a technique called Monte Carlo localization, and it's today the gold standard for robot localization. So basically, I don't want to say all systems because that's not true. There are also particle filter-based systems, but a large majority of systems, especially those which don't use predefined landmarks, use Monte Carlo localization as the localization technique. So to sum up particle filters, I know that this was a very short introduction to particle filters, and you may revisit particle filters again, either through the reference I will provide in the end through the book, or through the Introduction to Mobile Robotics course, where particle filters have been introduced more extensively. So what particle filters are, they are a recursive-based filter, and especially a non-parametric variant of that. That means that we don't have a parametric distribution, parametric function which we use to describe our posterior, but we use random samples to do that. And we draw samples from a so-called proposal distribution to advance to the next state, and then do the correction in order to take into account that the proposal distribution was not the target distribution that I want to approximate. And then the final step is a resampling step, and this is a technique which works very well especially in low-dimensional spaces. So the higher the dimension of the state space, the more samples that I need at some point in time, it simply gets intractable. Monte Carlo localization is a special instance of particle filters, so doing localization with particle filters, and it uses the particles to represent the pose of the robot, so typically x, y, and the orientation theta. It uses the motion model typically as a proposal distribution, and as a result of this choice, the correction or the importance weight is corrected with the observation likelihood, and this technique is called Monte Carlo localization, or in short MCL, and it's kind of the gold standard for mobile robot localization in robotics today in most applications. There are other applications for sure, but this is one of the standard choices. You find more on Monte Carlo localization in the probabilistic robotics book, on particle filter localization, as well as on the particle filter itself, depending on which aspect you want to focus on more. And in order to implement the particle filter, you of course need the motion model and the observation model. And these were exactly the models that I explained, I think, in the first week or second week of this course. These models are exactly the models you use in here, but here's again the reference to the chapters in the book if you want to revisit that. I know that was kind of a quick and not too detailed introduction to the particle filter, but I think it highlights the key most important things. First thing, we need a proposal distribution, which is used to generate the next generation of samples. And it uses typically the motion model. There are other choices. I can set those choices as I want them as a designer, but the motion model is a common choice. Then I have to do a correction step, which takes into account the difference between my target distribution and my proposal distribution. And this gives a weight for every sample. And I use this to correct for the difference between what I want to approximate and what I approximated so far. And then the third step is a resampling step. And these are kind of the key concepts that we need also to understand how SLAM works with particle filters. We just need to define a proposal distribution. We'll start also with the same proposal, the motion model. Later on in the course, we will say there are smarter ways for doing that or better ways for doing that, which then will also impact the way we compute the weights. And again, we will do the resampling step. These are kind of, so just focused on kind of a little bit on the high level concepts here in this course today. It's just kind of, whatever, half an hour, 45 minutes on the particle filter. But this should give you the basics for understanding what's going on in the future. You're of course happily invited to dive more into the details, but this can be time consuming to do that depending on how deep you want to dive. So that's kind of the minimum amount that you will need to understand the subsequent course. If this sounds really unfamiliar to you, or you think, I haven't fully understand it, I recommend you to revisit that until next week when we dive into particle filtering in more detail, especially doing slime or fast slime, which is one variant of doing slime with particle filters. But the concepts we have discussed here are kind of the key ingredients that you need in order to understand what's going on. Are there any questions at that point? Okay, so then that's it from my side. Thanks, and we see each other next week, next Monday. Thank you.